As we know, soil organic carbon is the key factor which influences soil physical, chemical, and biological health. Now, improvement in soil health is essential for its sustainable use with higher resource use efficiency. So, soil health is very important, and improving resource use efficiency, we have to improve our soil health, and soil organic carbon is the key factor for this. Besides improving soil health, soil organic carbon sequestration helps in the mitigation of adverse impacts of climate change and reducing the global warming potential. So now the 4P1000 and so many concepts are coming, and the basic objective is to improve carbon sequestration, mitigate climate change, and improve soil health, and ultimately it will lead to improve our resource use efficiency. Keeping this in view, our second lecture will be delivered by Dr. Dinesh Kumar Benbi, National Professor, ICR at Punjab Agriculture University. He is an authority on carbon sequestration and modeling. Now, may I request Dr. Benbi to deliver his lecture on soil carbon sequestration for improving resource use efficiency in agriculture. Dr. Benbi, please.
First of all, I'm really thankful to you, to Dr. S.K. Chaudhary, DDG NRM, and President of the Indian Agrophysics Society, for giving me the chance to be with you this afternoon. Now, as announced just now, I will be speaking on soil carbon sequestration and how this could be helpful in improving resource efficiency in agriculture. So basically, I would be, since it's a sort of webinar come training course, so I'll be trying to first explain how we really sequester carbon and how it affects our functions, and which ultimately affects nutrient use efficiency. When we're talking about nutrient or resource use efficiency, when we're talking about resources, we are talking about nutrient, water, and energy, which this is very, very important. And of course, when we say nutrient, carbon is one of the also nutrients when we talk about use efficiency. So this is one of the key things we will talk about. And as you know, basically, soil as a resource is under stress. Why soil as a resource is under stress? We at one time were starving. We had very limited access to food, and this was a global phenomenon, not only in India. India was one of the countries. And then there came a concept which was called a green revolution. And this green revolution was basically a great success. And we know it very well in India. Our crop production was about less than 70 million tons in 60s before green revolution. Now it's 380 million tons in this year. And you can see the big increase. And similarly, productivity has also been like anything from about 500 kilograms per hectare. Now we are talking about more than 3,000 kilograms per hectare. So basically, that means we have been able to really get one service from soil, the service of providing food to the people. And this has come at a price. If you see the world food production, to produce 1 billion tons of food in the world, it took us 10,000 years. But when we had this green revolution, technology adopted, which was like, say, we have improved one crop varieties, we have access to irrigation water, and even through private wells, we have mechanized agriculture, we have nutrients, we have pesticides, all those aspects associated with the revolution, they helped us in doubling our production within 40 years. So that means what we achieved in 10,000 years, we can achieve the same in 40 years. But this has an effect on our environment, our socio-economic impacts. And one of the most important things which we are talking about today nowadays is global warming or climate change. So it also impacted the greenhouse gas emissions. In these 40 years, our emissions from agriculture almost increased 35%. But at the same time, one good thing is that because this green revolution is associated with intensification of agriculture, so intensification also helped us mitigating greenhouse emissions. Had we not done intensification, we would have brought more land under cultivation. And because of land use changes, they would have more emissions. So that means in a way it has been helpful, though it helped us, or though it led to greater emissions, but at the same time it also minimized emissions, which could have been related with the land usages because of more land required to produce the same amount of food. Now, if you see what happened basically when we say soil under stress. So one thing which we say is soil under stress, most important thing which comes to our mind as a resource, soil as a resource, is nutrient depletions. When I said we had produced so much food, we had so much productivity per unit of land, we have now, if you take the case of India, now we have 143% as of cropping intensity. So that means we are taking harvesting about 1.5 crops per year. Like in states like Punjab, we are harvesting more than 2 or 3 crops per year. So that means we are mining nutrients from the soil. So that means we are having nutrient depletions. And because if these nutrient depletions, they are now causing so-called multi-nutrient deficiencies around all the soils. Now, if you look at an example from India, we have more than half the soils which are deficient in zinc and sulfur, and almost an equal amount which are getting deficient in boron. And there are some soils which are about 25%, 50%, 20% are deficient in other micronutrients. So that means we have an issue with soil nutrient deficiencies. That means declining nutrient use efficiency because of multiple nutrient deficiencies. Sometimes the deficiencies are symptomatic, you can see very quickly, so that you can take remedial measures. Sometimes you are working with so-called hidden hunger zone, where these are not apparent. If you are not able to see those symptoms, so probably farmers miss out on those applications, and then deficiencies, and then there is a decrease in productivity or resource use efficiency. Now, if you look at the world picture, from about 80 as the source of billion tons of steel production per ton of end use, today we are working with about 20 as an efficiency factor. That means per ton of land used, we are getting only harvesting about 20 tons of cereals. Same as the condition is in India, it is much, much worse. From 50, we have come down to almost 10, and still, though it's trying to stabilize, but still it is showing a declining trend. Now how this all affects them? That means what we are doing now, what we are trying to correlate is, say we have now nutrient deficiencies, we have nutrient depletions. Now soil performs some functions. We know it very well, and it's very well written that soil provides provisioning functions, supervising functions, supporting functions, regulating functions, or cultural functions. Now, when we say nutrient depleting, that means in a way we are saying soil health is going down. That means if soil health is going down, if you look on ourselves, if we have low health, if we have poor health, if we have problems with our health, our capacity to provide functions to our family, to ourselves, goes down. So we are not able to work in the same way in our office if we have poor health. So same is with the conditions of soils. Now when the soils are unhealthy, their capacity to provide those services like food, feed, fiber, fuel, water, and water, when we say water provisioning, as well as water quality, and its capacity to cycling for nutrients, and they all go down. So that means basically, and most importantly, soils perform a very important function other than supporting and provisioning, regulating. They regulate what we always look for: soil erosion. They regulate water quality, and most importantly, which we are talking today, they regulate organic carbon accumulation. And organic carbon accumulation is a key, is a central point which affects soil health, as well as nowadays very important topic we're talking about, global climate change or global warming. And so that means we are now have to really optimize our resource use efficiency so that soil health is basically maintained or enhanced, and we are able to get the functions at their optimum level. Now, soil, when we talk about soil functions, what are the properties we should aim at? Or because when we're talking about models, when we're talking about predicting soil's capacity to function, when we are measuring the field, so I mean, there are measurements, there are modeling issues. Now, what properties we should aim at? Now, just now you have heard a lecture on water, you know what are the properties that are very important. But when we're talking about nutrient use efficiencies and the modeling of carbon or the modeling of soil functions optimization, there are three core soil properties which are very, very important. One is soil texture, and another is soil mineralogy. Now, texture and mineralogy both are basically inherent properties, which we are called as static properties, which cannot be changed over years because they are the property from which the soils are formed, and how long it has taken place, and what is the soil texture after a given the time of weathering and other process, soil forming processes. But third key property, which is very relevant to us, which we can always try to manage, is soil organometer. This is a third core property. Soil organometer, it is dynamic, one thing, contrary to the next terminology, which is static. So that means it changes. Moment we make any interventions, so man-made interventions, management interventions, then we go for that. So that means we are trying to manage, or we can try to change the soil organometer content. And that means this is some good thing. But at the same time, we have to be very careful that if you have mismanagement, you can destroy organometer also. So we have to look for options where we can improve organometer. So that means this is a way, if you improve organometer, you are improving soil functions. And the specific functions which we are aiming at in soil, we are always have very well known three functions. This means soil carbon, which fuel these functions, I will say. So basically all those functions, or they are related to soil processes. That we know soils have physical processes, chemical processes, and biological processes. And these processes are ultimately also related to soil properties, physical, chemical, and biological properties, which we always try to study in the laboratory. As students of soil science, we are much studying the processes per se. We study the properties, then correlate with them the soil processes. So that means if you are talking about water and storage, bulk density, soil structure, in a way we are talking about soil water dynamics, soil hydrological properties we are trying to study, soil water processes we are trying to study. And they are very important aspects in water storage, nutrient management, and water use efficiency, which are related to soil's physical properties. Similarly, when we are talking about buffering or soil pH, cation exchange capacity, nutrient availability, nutrient losses, and most importantly, nowadays we are talking about toxicity and groundwater pollution. Even all these processes soil perform these functions, and where these chemical processes they are performed by soil because of certain key indicators which we just now talked about, the organic matter. Similarly, biological processes which make nutrients available through process of decomposition. So some biochemical processes which take place, and bioavailability of these trace elements. Now, when you look on these physical, chemical, and biological processes, they cannot be seen in isolation. They are all interlinked because physical is a habitat. If you're talking about microorganisms, physics is a habitat for organisms, and the water, air, they are the force behind their living. That's why chemical. When you're talking about organometer, when you're talking about nutrient availability, how they complex. The organometer makes complexity with nutrients. They complex toxic elements, and then that means physical, chemical, biological. They are interrelated. And their key property which interrelates them is ultimately the so-called organic matter. And then the net effect also affects carbon emissions, carbon sequestration, and ultimately climate change. Now, what is organic matter at a given time? Because for the modelers, it is always important to see that at a given time, what is the net amount of organic carbon? What we measure in the laboratory? Soil organic carbon, or total organic carbon, what we call as, or sometimes total carbon, when we have also inorganic carbon. So it is a net effect of inputs and outputs. Inputs are basically of two types, which one is basically what from a cropped field in agriculture or under vegetation. We have what is coming from the plant. And second is what is going out through leaching, erosion, and through decomposition process, what we call as mineralization. And then we can have also input of from bringing from outside, putting the soil, so exogenous input. So that can also add to organic matter. So net effect of the decomposition processes That is the loss process, which is output, and the input, which comes from plant as well as from outside. They determine what is the amount of organic carbon in a given soil. And land use and management, they affect all these input-output relationships. And our aim is always to look for how best we can optimize these two input and output processes. Now, when we look on input or output fluxes, as I said in the last slide, that you have plant-mediated carbon input. Now you have our plant biomass. Now this plant biomass captures carbon from the atmosphere through the process of photosynthesis. Now this carbon is captured. This was carbon dioxide, and this has been converted to organic carbon. So this is very, very important point which we need to note, that now we are converting CO2 to organic carbon through the plant, through the process of photosynthesis. Plant, half of this carbon goes back, what's a gross plant captures, half of it goes back as plant respiration. So that means on a global scale, if you are capturing 120 gigatons of carbon through plant capture, about 60 goes back. Then you have 60, which is retained in the plant. Now, out of this, up to 45% of carbon goes to the root through root exudates, root biomass. So this is very, very important. That means you capture carbon from the atmosphere, you bring it here. Part of it goes back as plant respiration, and part comes to the soil. Now here we are always concerned that we want to retain this in the soil, so that once whatsoever comes, how much we can really retain, so that lesser amount of goes back. And then this comes through root exudates. Then at the same time, plant litter, plant stubble which falls on that, they also add to soil organic matter. And then you remove some carbon when the harvested products, when you harvest the edible parts or parts which have economic value, when you take them away, you are removing carbon from that particular place. If that carbon is ultimately converted to some products which are permanent, we have sequestered carbon. But if they are not permanent, we have again brought the carbon back to activity cycle. So that's very important, how best we use that. So that means we have a fluxes which bring carbon, these yellow arrows you will see, they bring carbon and ultimately build up organic matter. And those fluxes, which these color, they show that carbon is going back. So we have to maximize these fluxes shown with yellow arrows. Now, if you look at the total carbon stocks in the world soil, after all this, doing all this, now what is the status of soils? They have been really various estimates of carbon stored in soil, and these estimates have been revising from time to time. Now it's assumed that, based on a lot of data analysis, that world soils contain about up to 1,000 gigatons of carbon. When I say gigaton, I mean billion tons of carbon in the top 30 centimeter soil, and up to 2,500 of gigatons of carbon in the 1 meter soil. And India accounts for quite a bit of amount of soil, about 2 to 3% of the world soil's carbon is stored in soils in India. So that means this is an applicable amount, and we have to really, this carbon which is stored in soil, it is not constant. It has also changed over years. And when you see what are soils which really contain most of carbon, if you see the world soils, we have 12 soil orders. Out of these, 5 orders, antisols, jelly soils, histosols, insectisols, and mollisols, they almost take care of 72% of the carbon, the total world soils. So that means out of 2,500 kilograms of carbon, about 72% is stored in 5 soil orders. And most important, about 1/4 of this carbon is stored in jelly soils. Jelly soils are soils which are under permafrost in Siberia, Canada, in many countries. You don't find it in India, basically. So that means they store a lot of carbon. So it's good that store carbon, but they are also a cause of concern, because when these soils are thawed, they are in permafrost. When the conditions are anaerobic, they are thawing, they emit methane. Methane has a much higher global warming potential compared to CO2. So that means we are at a risk of losing a lot of carbon through methane, and which can add to so-called global warming. And when they still keep on draining, and then when they attain aerobic conditions, they can still lose a lot of carbon dioxide. So they can add methane, they can add carbon dioxide. So those soils need special attention as far as we need to conserve or minimize carbon emissions. But Word of caution, I must say, there is a large uncertainty associated with all these estimates. They are not when the numbers, they are just estimates. That's why I said there is also range about 14% and something about 25%. So that means there is a large amount of uncertainty associated with all these measurements. And what management is doing to us, as I said in the very first slide, that our carbon, organic carbon in the soil per se, is a net effect of input and output analysis. Now, here is a schematic presentation which was appeared by Jensen in sometime in 1998, and this is still valid and very pertinent. When you had traditional agriculture, you were working on some carbon which was working somewhere here, soil carbon. So there was a steady state condition. You had certain soils under forest, some under natural vegetation, and then people started going for land use because we needed more food. So there was the harvest of grasslands, they were converted to cropland. And then when tilling soils, when cultivating soils, we started using carbon. So that means soils were using carbon. Most of carbon was emitted as carbon dioxide to the atmosphere. This was a time when we started bringing agriculture. Now, after decades, this new carbon, which was now we are losing carbon, there's a new stable carbon level. We attained that level, a new steady state. We had a steady state prior to land use changes. Now, after land use changes are imposing agriculture, we attain a new steady state, a new equilibrium, where we say now our carbon is stable. If we continue with those processes, with those practices, but we are now doing it at this time, now our carbon will remain steady at the same level, may not lose further. But if you try to go for still mismanagement, this can still go down. But now, if you put improved management, if you look for interventions which can build productivity, build up carbon in the soil, then you can work with something like this. Say you want to bring some carbon back. So you had lost some carbon here. Now with improved management, you want to bring that carbon back. How much carbon you can put it back? Because if can you do that? And what are those management practices that we'll talk about today? Now, if you look on Indian soils have lost something when you compare with non-cultivated soils, which are under natural vegetation, also called native soils, and you compare them with at the present level cultivated soils. If you compare those numbers, you can find that Indian soils have lost something about 30% to 60% of organic carbon, what they had at this level. Now, this is a big range from something about 30 to 60%. This big range because of climatic conditions, soil type, soil texture, and the management and the production system. So all these factors determine how much carbon you will be using, or you want to use much carbon. And if you look on many soils, some soils which are not converted from natural vegetation, they might have gained some carbon. That we'll see later on in this lecture. Now, when you look on the global picture, globally about 40 to 80 gigatons of carbon has been lost historically. In the last 300 years, there are estimates from 1700 onwards. So global soils have lost something about 40 to 80 billion tons of gigatons of carbon. And it is estimated that if you put improved management, we can at least, if we cannot bring all of it back, we can bring at least half of it, around 37 gigatons of carbon back to the soils. So that means we can sequester carbon. And basically what we say, potential with all assumptions, with assuming that how much land we can bring at a certain land use, how much a given practice can be imposed like CA or tillage or those things. It is estimated that about 20 to 30 gigatons of carbon in the next 50 years, generally estimates are made for 25 to 50 years, can be sequestered in world soils. And we have to keep this in the view that we are aiming at, as per Paris Agreement, 4%, 4 per million, 4 per 1,000, 0.4% of carbon sequestration. So that we see with that backdrop, can we attain that 4 per million initiative or not? Now, another important thing is when we say organic carbon, there is a circular relationship between soil degradation, soil health deterioration, and organic carbon. Now, if you look on this, so soil erosion is one of the degradation processes, and globally, about 1/3 of soils they are degraded, and erosion is the major cause. But if you look on the very basic picture on soil erosion, which was from Israel, you will find that nutrient depletion is also an important process through which soils also are degraded. And it is estimated that if we continue with the processes we have today, we can even degrade our soil up to 90% by the year 2050. And India has a quite appreciable amount of degraded soils, which have potential of carbon storage and carbon sequestration. About 104 million hectares of land in India is degraded. And erosion cover soil is 85 million hectares. And so with this is not only soil degradation, so with this is a socio-economic aspect also. When soil erosion taking place, nutrients worth about $9 billion every year are lost to the sediment. So that means we are losing nutrients from soil, and we are bringing them back by putting more money, by fertilizers, and bringing that back. So in a way, we are having two issues: economic issue as well as soil health issues. So economic issues ultimately have major bearing on crop production. Now, when I say it's a circular, when soil erosion taking place, where erosion has not taken place even, the soils in that particular field, they are also having major issues with organic carbon loss, because soil particles, they break down the structure, and when the structure is broken down, the carbon is all protected inside the aggregates, that is exposed. Once that's exposed, that is prone to decomposition very quickly, and soils start losing carbon. So that means we have a two-way loss of carbon. We are taking carbon away from a given site. On the same site, we are losing carbon through decomposition. And what are the, now, when I said that we can bring 20, 30 gigatons of carbon back to the soil, what is the principle? How to do it? As I said in the beginning, that we have to increase carbon inputs of soil, and we have to minimize carbon output or carbon losses. And then we have to simultaneously improve our resource use efficiency. What we say, water use efficiency, nutrient use efficiency, and energy use efficiency. And all that they will take care of our carbon sequestration issues. Now, there are a certain number of practices which have been recommended from time to time, which have been evaluated in different conditions for different countries, different regions, like what kind of land use we should use. Do we go for short rotation forestry, agroforestry type of things, or can we really go for intensive cropping, intensive agriculture, or can we go from monoculture to diversity crop rotations? And how much can we really introduce legumes in a cropping system where it's practical, or go for green manuring, organic manuring? And most importantly, where it is possible. Somewhere now in India, not everywhere is possible. How can we eliminate crop fellows? It's not very common in our country because we already have very limited land. But where it's possible, we eliminate fellows. And then, very important, which is also not only for soil scientists, also for plant breeders, look for crops which are deep-rooted crops, so that carbon is placed deeper in the profile. So it is not the surface layer. So if it is carbon surface layer is prone to loss very quickly. Carbon placed deeper in the profile would be retained in the soil, and which is much difficult to be emitted to the environment. And then how we can minimize or decrease our carbon output. Very importantly, just we now discussed erosion control, how we can control erosion, and then look for the processes which deteriorate, which expose the carbon to the environment, like erosion, tillage. Now, basically, we always try to say that more you till, the more you can produce. Now, our thinking has to change. We have to optimize how much to till, so that people now talk about CA, conservation agriculture. So how we conserve the resources. So that's very important. So that means is tillage, organic matter bring back. Conservation agriculture is basically a cocktail of the practices which I say increasing carbon input and decrease outputs. It's a combination. So that means we are now having harmony between inputs and outputs when we say we are going for conservation agriculture, also called CA. And then we try to really manipulate soil's hydrothermal regime. Now you can take help of models like hydroset, all those models. Go for the practices which maintain or temperature and moisture in such a condition that you minimize the decomposition process of the soil surface. So you go for mulch farming, minimize bare fallow, and go for more. So very importantly, You go for low quality input. When we say low quality input, we look for the material which doesn't decompose very fast. Material which are cellulosic, they decompose very fast. If you have material which decomposes slowly, so it will retain carbon for a longer time. So soil retention capacity, we'll see how in the later slides, how biochar can help. So how composting can help, because they have lower CN ratios, they decompose much slowly. Carbon, they have much higher so-called MRT, mean residence time. The carbon stays for a longer time. Now, when I said cropping system, just I'll take some examples. Now, important example is now you have lost carbon. Now you're looking for practices which you can say carbon rehabilitation processes. Now you want to bring carbon back. I say rehabilitation. Now, if you go for, let's say, the real example from northern state of Punjab, if you look on this, now if you impose agroforestry, after a few years, you see the rehabilitation with the agroforestry is 93%. But if you are bringing sugarcane, it's around 86%. But if you are continuing with maize wheat, rice wheat, with your improved management, still it is around 60%, 68% or 73%. So that means perennial cropping, or with cropping which crops which stay for longer in the soil or in a year, they have much higher rehabilitation potential than compared to single season crops. Similarly, now very important, this is a results from a meta-analysis published worldwide. Now a number of studies have been done. I try to put them together from that meta-analysis. Now it's apparently very clear. If you see this side, now when you are converting your land use from cropland to permanent vegetation or near natural vegetation, like cropland to forest, cropland to pastures, cropland to plantation, you are building up carbon. So that the numbers may vary from place to place, something ranging from 8% to 60%. You can bring in change in organic stocks in the soil. But if you are doing the reverse, if you are putting pastures back to cropland, if you are putting plantation back for cropland, you are losing carbon. Something about 50% to 80% of carbon could be lost if you are putting in permanent vegetation back to croplands. So that means the message is very clear that we are looking for this. That means can we really do some optimization, and these numbers, they would vary from soil type, what the reference levels of carbon was there to start with, and how intensive is agriculture. All they will determine. So in a way, we want to store this. We want to minimize this loss of 10 to 60%. We want to maximize this 8 to 15%. We should work somewhere in between this. And then another example, as I said, intensive agriculture is not a bad answer. Now, a real example from the North Indian state of Punjab. Those of you who doesn't know, now Punjab, the 3 states of India, Punjab, Haryana, and West Uttar Pradesh, they are the original green revolution states. The green revolution started from these states in India. And so they are the great examples where we can have case studies where you can see what is happening over time. Now, we have now this data for 25 years, something from 1980 onwards up to 2005. If you look on this, now if you see, if you are working with intensive agriculture, because Punjab is an example, where we have intensification at a very high level. Now, even today, we are working with 2.5 crops or 250% of cropping intensity. So that means farmers, they grow rice, let's say, then wheat, in between there is a crop, in between, or between wheat and rice, there is some other jad crop or summer crop. So there are mostly 3 crops in one. If you look on this, we always say when you go for cropping, cultivation, you lose carbon. It's not true. Now here, you see, we are building up carbon. The 25 years Punjab soils have shown there is a carbon buildup. We have almost 30% carbon buildup over the years. Why this buildup has come? So why it is contrary to that? Sometimes when we say 80s, we are working very low productivity, less than 7 tons or 6 tons of total annual productivity. And today in Punjab, we are working with a productivity of something about 15 tons per hectare per year. So when we have increased production or productivity, we have also increased the root biomass. We have also increased the root biomass. If you think back, that slide when I said the carbon fluxes plants capture carbon. Some more the carbon captured by soil by plants, the more is humidified and will be stored as organic carbon. So that means intensification in a way has helped us in bringing, provided we have rational use of water, nutrients, and tillage. Otherwise, you tend to lose more carbon. Now, if you see the global India's total attendance, all of you know that there are ICR has introduced so-called long-term experiments or long-term fertile experiment scheme project since 1970. Now, under this scheme, a number of experiments at different places have been conducted. The aim at that time was to maximize productivity with minimum fertilizer use. So treatments were something like 50% NPK, 100% NPK, 100% NPK, or N only, P only, K only, and then and so-called integrated nutrient management (NP). I try to put those data together from all the sites which we had. Sorry, so more than for 20 years. Now, when you compare with N or NP or NK, no balanced fertilization, or when you say no unfertilized, if you are going for balanced application NP and K, you are tend to build up your carbon. Your carbon content can go up to more than double, and your carbon stocks can increase by something about 20 to 600 kilograms per hectare per year. But if you top up this with organic manure, so-called INM, integrated management, you apply FIM, so your benefits are sometimes almost doubled. So you can store up to 1200 kilograms of carbon per hectare per year in soil. So that means these two practices, which are very simple to adopt, which all farmers are really find it easy without any problem. They could use to adopt so-called NPK plus manure and animal manure application. So we can really build up organic carbon level soils. Now, but we should keep in mind, I said, when you have a balance of organic carbon, the carbon brought from outside, plant-induced carbon and carbon brought from outside can build up carbon. We have to keep in mind. Now, papers appear, a lot of publications, they are shown that you have certain amount of carbon, your organic carbon content has built up or gone up. And sometimes, when I look at those papers, the amount of carbon added and the carbon built up is sometimes not in harmony. Looks like that you are building more carbon than what you're adding. If you look on all the balance sheets, you make a spreadsheet, you see this was by carbon captured through photosynthesis, this was a carbon which could have gone into soil. You go for gross productivity, net productivity, and then see how much is biomass. And you see the build-up is more than what you could expect theoretically. So, what is the catch? We have to keep in mind there is a critical carbon. If you put below that, here you see if you see this particular intercept of the x-axis, you will find that this is the value. If you go beyond this, then you start building up carbon. Below this, you can still use carbon. So that means in a condition we are cropping, we are cultivating. So that means you can still use carbon. So the plant-mediated carbon, let's say in this case, we had a study about 2.5 tons of carbon must be added every year, so that you can really maintain carbon. So I call it as a maintenance dose. So that means there is a maintenance dose up to which you can start seeing the effects. Before that, the effects won't be even visible. So you will be losing carbon. And then how much carbon remains the soil? Now I try to put the estimates from different studies and from India also. So I could find numbers something varying from 3 to 28% of the carbon to add is retained as well. 28% is a very high number. This is on the higher side. If you are working in the cold climates, so road decomposition, probably you attain that. By thumb rule, if you go, something about 10 to 15% of carbon, which is added to the soil, it remains in this soil. So that means you should aim at about 10 to 15% of the carbon, depending on soil, climatic condition, vegetation, and the management. Now, another important practice which I said just now about carbon sequestration was about tillage. I talked about conservation agriculture, I talked about tillage. Tillage is one topic which is, I think, now in very limelight. So because this is the process or this is the practice which is supposedly helpful, because they say that all the tillage functions are taken by the microbial activity in the soil. So you don't till, you let the microbes take over, and, and then improve your carbon content and resource use efficiency. Now, when you look on this tillage, we did some small experiment across farmers' fields. Now, the results are very interesting. When you impose tillage practices, very first 2 or 3 years, we have seen that we are losing carbon. Our organic carbon content has gone down. But after a few years, the carbon content increases. So that means the tillage effects are not visible immediately. It may take some time before you start seeing the effects. That's one thing. Secondly, tillage effects are not visible every year. If you look on this graph, you will see the effect is negative in some slides. Here, this is negative. That means you're losing carbon. In some, it's positive, big one. Some, it's very small one. So the effect is site-specific. That means soil property, which I said in the very beginning, the core soil properties. One of the core soil property in this case is soil texture. Soil texture will determine that how fast and how quickly you will get the effect, and then how long this practice will continue. That's very important. That means the length of the practice or when you continue, and the soil properties, they determine the response to tillage. And very important, another aspect related to this is tillage is not only affecting organic carbon. Tillage is affecting the soil physical process. Aggregation is very, very important. Compaction, work density, water dynamics, they are all controlled by tillage. And tillage ultimately, that means tillage affects carbon, hydrogen, oxygen cycles. Then carbon, hydrogen, when you till, you enhance those cycles. When you don't till, you slow down those cycles, and that means you are keeping those more for longer time. And another thing which you say when you are tilling or when you're not tilling, you have another very important aspect. For those who are maybe getting this training as students, or very important that how much soil to sample. Tillage is a big issue. If you are just sampling, if you're tilling up to 35 centimeter plot footage or the chiseling, and you are sampling only up to 15 or 30 or 20 centimeter, 25 centimeter, you are producing artifacts. So tillage leads to stratification. So we need to know how deep to sample to really make a conclusive statement about whether there is a really helping us storing carbon, or carbon has been really stratified in different layers with tillage and without tillage. So that has to be kept in mind. So that's an important issue. Then now we'll talk about the source efficiency. And I said the quality in the very beginning, the quality of organic matter or the quality of carbon which you add is very, very important. Now you can compare two very clear situations. Now, this is a glaring issue in particularly in North India, that residue burning. And residue burning, basically, the major issue is always with rice residue, rice straw. When you burn rice straw, you have a lot of issues with human health, environmental health, and with the soil health. So that means residue burning has issues with all three which you have talked in the morning also: soil, plant, animal, and human health. So that means now people are advocating different ways of managing residue instead of burning. So one is very simple. You plow it back, that return, put it back as such per se, and then see what happens. And then you have a lot of machinery involved in that. Second, now sometimes the advocate is you make electricity, make energy, or you make some byproducts like that. And one of the byproducts could be which comes as a biochar from different processes. Now, when you compare application rice residue with rice biochar, now you see this is the on y-axis I've shown carbon use efficiency. Now this is rice straw, this is rice biochar. When you convert the same amount of rice straw to rice biochar, add to the feed, you see carbon use efficiency goes like anything. You are working with something like about 0.15 of carbon use efficiency. You have about 0.6, 0.67. Though it is less than the theoretical value of 0.66, but still you are working with the carbon use efficiency of more than 0.6. So that means if you are aiming at it with carbon use efficiency, so you better off, you convert to a product, provided you should keep in mind that that conversion should not cost you more energy. It should not be counterproductive. So that means if you do that, you are storing carbon for a longer time. Now, we have done studies, I'm not showing it here. The mean residence time, this carbon stays in soil is much longer. If you compare with rice residue, it is 65 days. When you compare with biochar, it's 470 days. So that means that stays in soil for a longer time. And why this happens? Why you have high carbon efficiency? That's a metabolic quotient. That means the amount of carbon required from this is less. More carbon is converted to biomass. And biomass carbon, if you assume ultimately after death becomes soil humus, you build up carbon. So that means why you can explain when you add biochar, why you sequester carbon? Because you are decreasing the carbon emissions through soil respiration, and you are increasing carbon use efficiency, and more carbon is retained as well. But then second other issue related with that, what biomaterial you are using at biochar. That's also determines how much benefit you can get with carbon sequestration. Here is another one. If you put wood biochar and you compare with the rice straw biochar, the effects are variable. What kind of feedstock you have, then because the composition of feedstock, like rice straw, is more containing more silica. There are more silica oxygen bonds. So they minimize carbon, they bind carbon. The carbon lost is much less than if you took on wood biochar, it's more popular, things like that. There is more cellulose contains more hemicellulose. So that has much less effect compared to rice biochar. Now, when we're talking about carbon, nitrogen use efficiency or source use efficiency, we have to see everything in totality. We should not just looking on the carbon, which, as I said, soil processes, physical processes, chemical processes, biological processes. When you're going for residue management, now there are three options available with us. Now, one is you remove the residue. That means you take it away. You take it away maybe by burning, maybe just for animal use, or you put it in some other fields. So you take it away, you don't leave it in the soil. So that means you are working with a field which had no residue left from the previous crop. Secondly, you do a part of it on that. A part is removed for animal fodder or some alternative uses. And third option is that you don't remove it at all. Now here is this outer one is you don't remove, you put it back in the field. The other one is that partially you remove, partially you leave in the soil. And third one, which is very, very dangerous, you remove all of it. Now, if you see what are the functions or what are those processes which affect the source use efficiency, they are affected. Now, if you are not removing, you see all those processes like nutrient cycling, water availability, thermal regulation, and groundwater recharge and its quality, I would say also, and erosion control, and they are all positively impacted. And most importantly, which they affect ultimately the biomass production and biodiversity, biological activity. So that means all these processes which affect these two, which we are always concerned about, they are at the highest level. So that means bringing the residue back, residue recycling, which practice is now disappearing slowly and slowly. So we should be aiming at that. And when you remove all of it, so all these processes are negatively impacted. You may have some impact on greenhouse gases. You may have some impact pest control because you have removed everything. But when you do this, so you have to be careful with your what I will say, the effects which could be negative. That means you try to minimize those, particularly pest control. You may need better options for that. Otherwise, so probably clear that we have seen that when you bring the carbon back through residues, or when you manage residues in such a way that they remain in the field, most of the processes which affect resource efficiency, they are optimized, and we are working the better soil health. Now to sum up these carbon sequestration practices and how much effect they could have, I try to put many studies together just to route out a rough estimate. That this question is always asked: if I do this, how much carbon I would store? If I do this practice, how much carbon I would store? Now, and this becomes more relevant, as I said in the just very beginning, that world soils are seen as a moderator of carbon change or to mitigate global climate change, and with 0.4% carbon as a target to keep temperature rise within 1 degree to 1.5 degrees centigrade. Now, you see, if you go for as an agroforestry, afforestation, all those things, you can do something about 0.6 tons of carbon per hectare per year. And if you go back, as I said, the land use practices bring to pasture land, again 0.5, and INM, all those things, 0.5. So if you look on this, a range of values, you will find something about 0.2 tons of carbon per hectare per year, up to 0.6 tons of carbon per hectare per year could be sequestered in the soil. But these are these effects will be site specific. That's very important. And then you can have a cocktail of practices. We should not see each practice in isolation. Probably there will be a combination of practices to combine together to attain greater benefit. As I just showed the example of balance fertilization and INM, they could be combined together. Now this brings me to the second part of our lecture. I mean, this was first I said how to sequester carbon. Now I would say there is a nexus between carbon sequestration, soil health, and resource use efficiency. So they are all interrelated. So you can read from carbon sequestration to resource use efficiency. You can read from resource use efficiency to carbon sequestration. So they all are interlinked. How they are interlinked? Look on this. Now, as I just now show, I will discuss this part, that how this plant this improves carbon sequestration in soil, and this how this carbon sequestration ultimately affects our soil health, and this soil health how it affects soil functions, and soil functions how they affect the soil sequestration ecosystems. Now let's talk about how they affect our resource use efficiency, which is a key to sustainable agriculture, or what we call as sustainable development goals, to increase more productivity and increase the resource efficiency. And if you see this, when I say resource efficiency is nexus, so when you have soil, better soil, you go back again, you have better productivity, and you have again cycle repeated. So that means ultimately again resource efficiency improves. So that means they are working in a cyclic manner. Now, some examples for this resource efficiency and how any carbon or soil they improve resource efficiency. These are real experimental examples I am showing you. Now, if you are sequestering carbon and your carbon is building up, now here is your organic carbon built up with time, or you had certain organic carbon levels in different soils, and here you have how much fertilizer you add to attain a given yield goal. These are yield goals. You want to get 2 tons, 3 tons, 4 tons, or 5 tons per hectare. So if you want to get a given yield goal, you see your amount of nitrogen required to attain a given yield goal goes down as our carbon content is increasing. So that means with increasing organic carbon, the amount of fertilizer required will be lesser. For a given, let's say for a given yield goal, if you are working with a carbon content of let's say 0.4%, so you need something like this. But if you are working with a higher yield goal, you may need more. But at the same time, for the attain same yield goal, if your carbon content is much higher, so that means maybe some places you don't need any fertilizer. You see here, you need, if you are working for 5 tons per hectare, at this you don't need any fertilizer application. So that means we have now 2 benefits. One benefit is that you need less fertilizer, less burden on farmer economically. Secondly, you are emitting less greenhouse gases while manufacturing fertilizer. So less fertilizer to manufacture, less fertilizer to transport, and less emissions per se in the field. So that means you are mitigating emissions and improving resource efficiency. And we have made simple estimate for soils in northern India. You can save about 4.75 kilogram of nitrogen, which could be applied to fertilizers, if per ton carbon which you store in only the plow area. And to back up with this, if you try to see, your productivity is also going up. So you see crop productivity as carbon is building up, productivity is also going up. There are reports of different crops and how associated stocks they change, and per ton increase carbon. So we say about 42 kilograms per hectare of crop productivity goes up as you build up carbon. But you keep in mind that the gains as you build up carbon, the effect is getting less and less. So that means you get much higher effect at low carbon levels when you build up there. Then that means that this also indicates how to prioritize for your carbon interventions. Then similarly, how I talked about biochar and how it affects carbon use efficiency. It also affects the source use efficiency of not only carbon, it affects nitrogen use efficiency also. When you go for this application, it also nitrogen priming from the soil. Soil nitrogen is really made more available through the agency of microorganisms. And that means if you apply residue, you see you have net immobilization. Nitrogen tagged with the residue because of vital C ratio. When you apply it as biochar, your nitrogen use efficiency, your nitrogen priming effect is much higher. So you get better nitrogen effects, and that means you again need less nitrogen application with this practice. Now, another source is phosphorus, very important. Primary nutrient, phosphorus. Same effect as I showed you about nitrogen. We also, there are different yield goals. Now, and there is amount of organic carbon soil and the amount of phosphorus fertilizer required. Now, as you are increasing your organic carbon content, for a given yield goal, your amount of fertilizer required is much lesser. And I tell you here that this observation, we have now introduced our soil health card or given to the farmers for fertilizer management. We tell them that if your organic carbon is this much, how much amount of fertilizer you have to reduce for phosphorus as well as for nitrogen. And then third resource, again another example, water use efficiency. The effect of organic carbon on water use efficiency are more glaring under dryland agriculture than irrigated agriculture. Because under irrigated agriculture, water is not a constraint. So generally, we are unable to see those effects. But if you see under dryland agriculture, you can clearly see here you are working with a carbon content of, let's say, 0.2% of organic carbon. Here you are working with a carbon content of 0.4%. You can see yourself how the productivity has gone up with the same amount of water application. So your productivity of the same amount of water availability to rainfall, your productivity is much higher. And because water use efficiency has gone up compared to when you're working with low organic carbon content. Now, up to now, we talked about all those measurements. Because since this seminar is about modeling, so I try to introduce a few things about modeling. I wouldn't be going into too much details because I know there are lectures on modeling, specialized lectures. So I wouldn't go into the intricacies of those modeling aspects. But for those who are interested, basically, how models have been used. Now, first of all, you must keep in mind what we have discussed so far. I have been saying time and again, they are site specific, they are management specific, they vary from place to place, they are climate specific. So that means we have so many complexities involved in carbon storage. So one thing is you do measurements every year and try to see, but again you are handicapped with predictions. You don't know what will happen. What if scenario is not available? You know what has happened over time, but you don't know what will happen. So you need to make a lot of measurements over time before you predict what will happen. So that means these carbon dynamics in soil, they are complex, both spatially and temporally. So that means we have to cope up with this spatial temporal variation. And for this, models they can help. Models are really always helpful that they try to take care of these variabilities, they incorporate in their domain so that we can predict what will happen. And when we say temporal variations, though that means we say, first of all, the carbon changes are not obvious in 1 year or 2 years. It's very difficult. In fact, if I add this word here, there are no single season or single carbon models available. For nitrogen, you can find some single season models. For carbon, they are not real single season models. There may be some lab studies available, some lab experiments modeled, but for predictive purposes, they are not, because the changes are very, very slow to occur. And then another important thing which I used to teach in my modeling class for course 502, and my professor in Germany also told me, the models, they help simplify reality. So keyword is simplify reality. But the problem is that the models have become more and more complex. So instead of simplifying, sometimes it becomes really difficult. Model itself becomes a big complexity. But fortunately, we have range of models, which are both simple in details as well as very, very complex. So basically, the aim is we should know which kind of model we want to use. What is our aim? For what we want to use this model? If you're using a model for academic purposes, for research purposes, you want to understand the process, you would look for a complex model. You look for which takes care of all the processes involved in that. If your aim is for farmer advisory purposes, you look for a simple model. So that means you look for models which are suitable to your objective. And when we say simple models or complex models, we can have simple empirical equations, simple function relationship, or we can have models where the biology processes involved in that. And they take care of all these smart processes, plant processes, or they link with other models to simulate a given aspect which they are not doing themselves. And the models also, when I say spatial ability, models also work at different scales. You can work on a laboratory, within a laboratory. You can work within the field at a microsite level. You can work at ecosystem level, or you can work with global level. So that means models, they have a range of skills on which, again, we have to see whether we're making prediction at the country level, or we are making prediction for a given field or for a farmer. So that has to determine our choice of the model. Now, when I say empirical complexity, examples of complexity, I said empirical models. Now, empirical models, simple regression equations. Sometimes the equations have a functional basis. Like you can develop a equation with the time versus calendar year versus crop productivity, calendar versus let's say given state variable, change in carbon or change in water content. So they are simple empirical models. But you can bring in more functionality. You can, instead of going say calendar time, you can have thermal time, degree days, growing degree days as one of the variables. So you can bring more type of biological meaning to your variables than just no biological meaning. So that means empirical model could be both functional as well as simple empirical formulations. And but the best thing about that, these models, they are more working on a push button philosophy. You do something, you get something. You don't know what's happening inside. More like a black box. So but they are more simple to use. So that means you can use them very easily, but within that black box, what's happening, it's difficult for you to know. Then second type of model, which we always are using now, very common, very popular. They involve the processes of carbon nitrogen dynamics. When I say carbon nitrogen turnover, all of you know that carbon nitrogen cycles, they are interrelated. So most of these models, they try to put carbon nitrogen together. So that means because they are interrelated cycles, so they try to partition carbon or organic carbon or solid matter into different conceptual or imaginary pools. So they develop certain models. Some models, they say based on C and ratio. Some they have certain hypotheses that this carbon is protected carbon, this is unprotected carbon, this is coarse carbon based on size, based on. But the issue is always there. They try to put some decompression rates that all of them, they use first order kinetics to predict decompression, but then they put rate modifiers, that they modify the rate of decompression. So as a effect of texture, as a effect of many models, they do texture as one of the variables, or as a effect of moisture content, or some other variables. They modify the temperature. But the major issue with these models is that there have been many modeling exercises where different models have been compared. The process-based models, they bring us to an important point that these pools, so-called conceptual pools, or imaginary pools, which I say, sometimes many of these pools are not measuring. There was a long time ago, there is a specialist of geothermal, where their results are published on modeling exercise held in Braunschweig in Germany. And a number of models they were compared. The one line conclusion I could say from there, that except biomass carbon, none of the models pools, they are measurable. You cannot go back and work and check whether you can measure those models or not. Except one of the models, SNBC, all of the pools are imaginary. Either you assume something, then you go to the next model, and the next pool or next pool. So then there was a statement in one of those papers, which I always repeat: modeling the measurable or measuring the modeling. Do we need new models which would put measurable pools? Because since then, our knowledge on carbon pools have improved drastically. Now we know very well what models or what pools we are measuring, what they are doing. Recently, we did a modeling measuring exercise. I think all of you are aware. They published a paper in Swan Biology Biochemistry last year. We compared 20 schemes of fractionation automation around the world, and these people from Germany, the Popolo and Axel Daum, they were the leaders in that, and our laboratory also participated in that. We tried to compare all the published modeling measurement schemes. We would try to measure carbon model pools or carbon fractions, And the laboratory from which most of these schemes emerged, they were asked to do a same samples analysis, do fractionation. And we were surprised that we got very different results. And none of the foods which we measured, they were able to trace 100% of the carbon turnover, though with good schemes, we could do up to 75% of the carbon turnover. We could trace that. Now, that is for now, there is a special website available, software.com, for those students who want to start their job research. They could see that site where we say which fraction scheme can help you identify your models, depending on your carbon fractions, and how you can use them. But the take-home message is that now we have different fractions available. They fraction at different aspects of carbon, but we have different rules which are in the models. How to reconcile that is a challenge. We have to see both for the modelers and for the people who are involved in the message. Then comes third category model, which we call as food web models or food chain models. They also similar to carbon fluxes, similar to process-based models, but they go towards the organisms. They go towards food web models. That means how the organism they utilize carbon. That means they are now more concerned about the resource use. Resource use is mobilization and immobilization. But they are basically aimed at modeling or simulating specific activities, management practices, specific management interventions, how they affect the food web, how they affect the biodiversity, how they affect the growth and decay of the organisms. So then basically they are there. Then the fourth category, the models, landscape, which are now very commonly being advocated, are being used, and they involve models which are simulate moisture dynamics, and the moisture dynamics ultimately affects carbon nitrogen dynamics, and they are more involved with the transport of nutrients, transport of carbon, nitrogen, dissolved organic matter, and all of those which control the different processes. It's beyond the scope of this lecture to discuss all these, but those who are interested, I'll later on give a reference. They can discuss, study on these. Now, three commonly used models, just wrapping. I'm not telling you to use these, but most of them, if you see publication, a lot of coming. One model, sensory, very commonly used. As I said, this model, process-based model, it also has 5 components, 5 tools. Argument is divided into, say, called metabolic and structural components. How you measure them, I don't know. And then you have so-called active and passive tools or passive model fractions, metabolic, structural, active, passive. And in this case, as I said, they impose some rate modifiers. So rate modifier in this case is they take the clay content, also texture, one of the modifiers that can be used to slow or enhance the carbon decomposition rates. And this model has been very commonly used to simulate long-term organic matter dynamics. And they also involve plant growth and not only carbon, they involve the sources, nutrients like NP, sulfur, all their cycles are involved. In a way, it's very good. It's a complete package, which I call these models as modeling packages. And very commonly, another very commonly used ROS-C model, Rothamsted for Rothamsted. It's different versions available, and they have been now updating all the time. Again, they also assume 5 tools. One is decomposer plant material, DPM, and recalcitrant plant resistant plant material, and then they have microbiomass. Then they have humidified and inert organisms. Here it is now again. If you look on this, they have certain partition coefficient based on certain studies they did years ago between DPM and RPM. They partition your carbon which is coming from a plant into 2 pools, DPM and RPM. And how to determine that is difficult to know. Probably you can do this, but you're certain about the experiments. You can fit 2 first order candidates with 2 pools of first order. One is decomposer, another is recalcitrant. Then you can get 2 rate constants, K1 and K2. Probably you can fix up those and partition this. We have tried to do that in our laboratory also to partition DPM by measurement. Biomass you can measure, and humidified and inert is difficult to measure. Inert organic matter in one of the publications is mentioned as a parking lot. Where also you are unable to simulate, you put to inert organic matter. That means this is not fitting into your scheme of things. You say this is inert organic matter. Basically, this is not easy to measure that. And again, similar to sensory, it also has some rate modifiers. And again, they are more talking about soil texture as one of the rate modifiers. And this model is basically, keep in mind, it's not for lowland soils. For paddy soils, it's difficult to use. But though it has been used and with certain modifications, but if the soils are submerged over time, so it's difficult to use. But basically upland, and it has been used worldwide for forest, temperate grasslands, and applicable to a lot of variable farming also. And third, which is very commonly used, DNDC model, denitrification decomposition model. As the name indicates, it very strongly simulates carbon nitrogen processes, and it is also, contrary to other models, it is also simulating emission of greenhouse gases. This is very important. And again, it has also what I call as different pools: labile resistant microbiomass, labile resistant passive pool cements. But I couldn't find a way to measure all of them again. So you have to background models, do iterations, and to bring a base level, and then you run those models. But basically, it has really given very good predictive capabilities. And this model has also good thing. It has inbuilt crop growth model also, so you can have also crop parameters, crop growth dynamics that can be taken care of. So, and it is also giving you the soil's carbon nitrogen balance. And what is the carbon sequestration potential of this model? That's also very important. You can get from, but you can get from raw sea also, other models also, if you know how to use them. We try to compare these two models for a given set of conditions. We use for rice wheat and maize wheat, and where we did two interventions. Let's say, because I showed in the very beginning, NPK, balance NPK, and you go for integrated management. How these models predict with time what would happen. Now, if you see both these models, they predict that you would be able to sequester carbon up to a certain level. Let's say raw sea says NPK, you can sequester that much amount of carbon after 1 year, after 5 years, after 10 years for a given rice wheat system. And if you are adding integrated management, your carbon sequestration will go up. So in a way, what I want to show from here is they are not telling you in 10 years whether you have already attained a potential or not, because it tells you what the potential of your given management for a given time scale. And if you look at DNDC model for the same soil, DNDC model slightly gives higher sequestration with the given management compared to this. But when you go manure application, so it is lesser than that. That means there is certain difference in their underlying concepts which are taking care of the organic matter or manure application. And then you can compare these models on basically the application. You can compare models for management comparison. You can compare models for looking for which is the best cropping system in a given condition. So you can see for a given soil, if you can go from 8.2 to 9.1 with the maize wheat, you can go up to 11.2 or 7.5 with the rice wheat. So you can also select what kind of cropping system could be good, what kind of management could be good with using these models. So that means you can generate what if scenarios. Now models have been, as I told you, models have, when I say scenarios, people have tried to use different scenarios using different models. And then they say low scenario, medium scenario, high scenario. They say an example for Indian soils using a medium scenario, which says that 0.2 to 0.9 tons of carbon per year in the 30 centimeter soil could be sequestered if you use a medium scenario. If you go to that high scenario, the numbers sometimes double up. So that means you have to be realistic. And then you correlate with what you actually see in your field conditions. So that means our agronomic research would validate this or not. Then another issue with modeling is upscaling of results. I think I'll finish. I'm not overshooting my time. This is how you do these models, how to take to different levels, how to extrapolate results. Now, basically, it's because one of the major issues with modeling is data availability. It's very difficult to get data. So, and particularly with soil properties, it's really difficult data across different regions. Let's say if you want to run a model of pan-India, or how to get all those data. Now people have tried to find a way out because data are always constrained, very difficult. Now there is another way, what we call as meta-modeling. It is different than meta-analysis. Keep in mind, we are not talking about meta-analysis. We are talking about meta-modeling. It is a statistical procedure. We will try to derive relationships between a certain variable as well as we get some output from process models. So we try to correlate process models and the output. Then output we interpolate and try to develop more data points. those data points that we try to use, like crop productivity versus moisture content. So these side of things we try to do with meta modeling. So those who are interested, they can go for all these things. And then there are two good examples I have putting for those who want to see. There's a paper from Florin in precision agriculture in 2011, and from Wang, where they use the meta modeling using Rossi model and AppSim model. They try to use meta models to generate more data. And then another option with your modeling is you try to prioritize soils which could store more carbon. You try to use our models, then see soils with more silt and clay content. Now this is so as silt and clay content is increasing, your carbon sequestration potential is increasing. What is basically we're trying to see what is the deficit in carbon sequestration. So you see these soils will be better off. You want to prioritize your intervention. You have limited money, limited resources. Here you can put more carbon compared to where if you're working with the low silt and clay content. And ultimately, what are the recommendations about the caveats involved in this? I have just 2 slides on that. One is we should keep in mind, as I showed in the last slide also, that capacity to sequester carbon is finite. We should not aim at infinite capacity, that we will just keep on putting things. And we cannot bring everything back to the soil what we have lost. As I told you, there is a certain capacity of 20 to 40 gigatons. So that with great efforts, probably we will do there. So we must be aware of what is the capacity for a given soil, how much carbon we can sequester. And then the sequestration which we do or carbon which is stored is not permanent. It is prone to loss once you withdraw your management. So that means you need to have a strict monitoring of carbon sequestration which has been claimed or which has been achieved. And then very importantly, you should be very careful when you sequester, is it carbon is just coarse particle matter which is still under transition, which will be lost very quickly, or which is still transforming, or you are measuring the resistant carbon. So that quality of carbon which has been stored, what we are about carbon fluctuation, that should be kept in mind. And what is its impact? How the carbon is sequestered, but how the climate variability in future would affect these results what I have talked about is not known. It's still uncertain. And moreover, the carbon sequestration which I projected that 0.2 to 0.6 tons per hectare, it's all biophysical. We should also keep money into consideration. Economic viability is very, very important. And then we should keep in mind always, we started with the green revolution and I with the green revolution. As I said, green revolution has been a great success, and we sequestered carbon, but we need to make a carbon footprinting. So looking only just soil carbon stocks is not sufficient. I talked about the state in Punjab. If you look on this, our sustainability is going down. Though carbon sequestration is going up, food grain production has gone up, but sustainability per se has gone down because of these practices which consume more fossil fuel, more carbon, more groundwater, more resources, pressure on that. That should be keep in mind. And those of you who are interested to know more, there are 2 books available which talk about the soil processes and its modeling, and the carbon and nitrogen processes and its modeling soil system. They can be consulted. Most of these things they have been covered in that. Thank you very much for your attention. I'm grateful to the audience for giving me this time. Great. Thank you.
Thank you, Dr. Benbi, for such an interesting and informative lecture. And I hope the delegates must have been enriched by your rich deliberations. There are some questions are also there.
Yes,
that,
okay.
If you could spare some time.
Yeah. I'm trying to get back to my how to get back. I'm unable to.
You may unshare your.
Yeah, sure.
One question by a delegate. Could you please name some process-oriented models for carbon and nitrogen simulation? That already
I've already shown the 3 examples basically.
You have already shown. And
in fact, there are many more. In fact, I try to avoid putting too much things.
Yes.
There are many models. I'm not biased towards saying Century or Rossi or DNDC. Or there are models which are also related to this and gas and all those things, even AppSim, and there are many models. Candy from Germany, and there are several models. And I must add here, it is easy to develop a model, then validate this. Validation because of data availability, data constraints, models have been less validated than developed. A number of process-based models are available, and more of them, the major difference between them is how to partition carbon into different pools. That is a major difference. Otherwise, processes are more or less modeled in a similar manner, assuming first order kinetics.
Sir, I have a question, sir.
Yes.
Now the concept of 4P1000 is coming.
Yeah.
In tropical situation like India, is it possible to achieve this target with our improved management practices?
This, Dr. Bandopal, this is a very good question.
Yes.
I think this is the most important question we need to answer. Basically, we say our flux is 800 and divided by 24. So we attained a value. Let's say this is a carbon stocks, this is a flux going every year. So divided by that, we attain a number 4. Where is the soil involved in this? You take local carbon, you take local fluxes. Where is carbon in India, carbon in USA, carbon in Germany, with different conditions, cannot store 0.4% carbon. What is my aim was time and again repeating, what is the anticipated carbon level? What are soil properties? There are some places it may be more than 0.4%, some places it may not be able to achieve. So that means we have to be realistic while talking about carbon fixing goals. The goals should be keeping in mind the resource, the soil as a resource. The resource with the farmers, the resource as natural resources, all the determined. And 0.4 is, I think, not very pious number. We should be very, very careful. Okay, this is an indicator that soils has important role to play in mitigating the CO2 flux. But the whole flux which you are trying to mitigate through soils is probably, I would say, not very realistic.
Thank you, sir.
Yeah.
If any delegates or if any...
Yes, I have a question.
Dr. Mohanty. Dr. Mohanty from Indian Institute of Soil Science, Bhopal.
Yeah. Sir, namaskar.
Namaskar.
Sir, I have a small question regarding the use of DNDC and ROTC. You have shown a slide where the simulation was carried out from 1 to 10 years. Rice wheat as well as maize wheat system. Sir, have you done any simulation of different levels of residues, maybe 2 tons, 4 tons, 6 tons? That actually why I am asking so, because if you consider the conservation ecosystem, or maybe, where we are adding a lot of residues to the system or incorporating in the rice wheat system, then what would be the amount of carbon that is sequestered through this by using these models? So your presentation is only rice wheat and maize wheat without residue addition.
We have that residue also. I mean, I've done many studies with that. This is I think, a very interesting question. Let me tell you, most of these models, they have issues with residue management and mulching. It is most of these, they are not really directly trying to address this issue. But at the same time, as I told you, if you are trying to do, let's say, processing, if you're trying to manage that residue, simply again, you have to partition this into 2 pools, DPM and RPM. And the issue becomes that we faced DPM RPM, that means the moment you add, instantly becomes DPM RPM, decomposer plant material, resistant plant material. And it may not be instant, right? So most of these processes in these models, they are assumed instant. Maybe you can do, if you are doing residue management, you cannot say that I have added 5 tons, 4 tons or like that. You can always do in terms of carbon. Carbon as DPM, carbon as RPM, because these models they simulate carbon added from a plant. You can add your residue to the plant carbon. When you are filling up input data, minimum data set, within that you can manage with this. It is possible. So you can do that. But again, sometimes what happens, your decompression rates become so, I would say, different. So you get results which are you feel is unrealistic. In the field, you don't change any carbon within 1 year. The model will show you change in one year. So that means you find it difficult to validate your results. Maybe if you run the model for 5 or 10 years. And if you have data for residue management, then you will be able to iterate, go back to your partitioning of residue. And residue partition again, their RPM, DPM is barley. You are working with rice. You are working with cotton. So your DPM, RPM will be drastically different. But you can play with these models to attain, if you have data for validation for the time period you want to run the model. So you cannot go beyond your time before that.
Okay, sir. Thank you so much.
Okay.
Thank you.
Okay.
Thank you, sir. There is another question by one of the delegates. can we predict carbon sequestration accurately in wetland situation which is high in iron and manganese content? In that situation, in the wetland, can we predict carbon sequestration accurately? And
in fact, this is a question, half question, because we are not talking about iron only, iron or manganese, whatsoever it is. In wetlands, we also talk about methane emission. So we have issues not only CO2, we have issues of also CH4. So there is much more difficult. Like modern DNDC, they have been used, and that could be used. But when you say accurately bird doesn't work in modeling patterns. If you are getting, let's say, 70%, 80% prediction, this is good enough. This is very good enough. You can never go for 100%. No models are complete. So you cannot work with the E equal to MC scale, right? So you always have a certain amount of uncertainty involved in that. Yes, I would say answer is yes. You can use models. Models are available for wetlands with certain degree of uncertainty. It could be predicted.
Thank you, sir. There is another question. If you would like to respond, he wants about the decomposition of plant material and resistant plant material.
Yeah.
Means DPM.
Yeah, DPM and RPM.
Is cellulose or RPM is lignin?
Basically, this is again a black box.
Yes, sir.
If most of this comes from laboratory experiments, you conduct a laboratory experiment, and then you keep on measuring it as a function of time, CO2 evolution, right? Or changes in soil organic carbon. If you measure CO2 evolution, so you plot these as cumulative time and cumulative CO2 evolution, you will find there are two peaks. First peak is about DPM. Then you estimate a constant for that. That is decomposed plant material. And then second part of the line is RPM. And again, this RPM could be exponential. This RPM could be linear. That's why we have two types of model: first order two compartment model, which could be first order zero order and first order first order. So basically, the aim would be to run your equation long enough so you get two pools separated. Then you estimate K1 and K2, or K DPM, K RPM. And then you have two different potentials. You add them up, you have total mineral potential, and you have DPM and RPM. Otherwise, there is no way to do that. Basically, but people have tried to correlate that what you decompose the first few days, they are water soluble carbon components, cellulose, and part of M0s. But at the same time, keep in mind, all materials are simultaneously decomposed. But prominently, water soluble components and cellulose, they are the first one which appear in the DPM fraction. Other less decomposed materials, they come, and basically there is a chain. If you look at the biochemistry books, there's a chain of decomposition. First comes cellulose, then these are the water soluble components, cellulose and cellulose. The DPM, RPM also follow the same chain, but it is an integrated effect. What we measure normally.
There is another question by Dr. Nishant Kumar Sinha. He is a young scientist from ISS Bhopal. They are working on DNDC. What they are getting, initial jump in simulated SOC compared to the observed, both in Rothsey and DNDC. Can you comment on this?
Sorry, say it again.
They are getting an initial jump in simulated soil organic carbon compared to the observed one, both in Rothsey and DNDC.
Basically, they have not run the model in a proper manner. You have to run the model 10,000 years back, bring it to the level where you have your measurements. You have to match your input and carbon status at the time you want to start your study. So if you have to go back, you have to go back iterations. When you go back iterations, bring it to level where you are working. Otherwise, you start the wrong measured value, or I will say different measured value, different predicted value. So your results will be different. So basically, you must match starting point.
That we have adjusted. That we have adjusted actually, but when you go for suppose future 5-10 years, we found that initial first year value is higher than suddenly jump in the value, then they stabilize slowly as the time progresses.
And
so
first year also you have measurements. You have measurements also in the first year.
Yes.
What is your measurement for total carbon? What is your measurement?
Total carbon and carbon stock actually.
Basically, total carbon and carbon stocks measurement in 1 year. I made a comment in the very beginning. Carbon measurements and modeling for 1 year is very unreliable, very difficult. If you get more uncertainty, more variation, as well as sampling and measurement, then you see the real change. So 1 year change, if you try to measure, even in the laboratory studies, they are not very reliable. I would always say carbon study should aim at a minimum 3 years. Before that, you will see the results are trustworthy.
Sir, that we have seen actually for 10 years value. The first year only there is a big jump. Otherwise, in second, third, fourth, fifth, in time series scale, the first year the jump was there, but second, third, fourth onwards, it was not that much high. We are not getting that high value.
After 10 years,
the first year, that is
after 10 years, okay.
10 years, it is stabilizing slowly and slowly. It is giving good result actually.
Yeah.
But first year result, we got suddenly jump in.
But then,
so we adjusted the 10,000 years
1 year, you look on your output, where the values are really absurd. You look for, then try to manage that particular aspect of your input. Then you will be able to do that.
Okay, sir.
But otherwise, I would always tell my students also, 1 year carbon measurements, 1 or 2 years, and more. You cannot give a management practice to a farmer that after 1 year you will carbon measure 3. You always look for long term, medium to long term.
Yes, a long term I was talking. Okay, sir.
Thank you, sir. Thank you for your response. Actually, a person who has himself worked in his own hand, he only, like a person like you, only can explain those things. We are highly enriched by your deliberations and your lecture, sir. And we thank you for your kindly accepting our invitation in a short notice and enriching us with your lecture. Thank you, sir. Now
Thank you, Dr. Benbi. I'm really thankful to you and great. If anybody has any questions to ask later on, they can just send me a WhatsApp or email, whatever they want.
Sure,
no
sir. Sure, sir. Sure, sir. We'll be in touch with you, sir.
Thank you, sir. Thanks a lot. It was great.